Hi everyone, thanks very much. So yeah, I'm going to talk about trying to connect. I know we've sort of, in this room, there's a big range of different topics, but here I'm going to try and draw the connections between planet formation and actually a much broader sense of astronomy and astrophysics in terms of connecting to the star formation environment. So we've seen these pictures, these images a couple of times from ALMA. These dust disks that ALMA has been discovering regularly, these substructures in the dust in the continuum. But I've just come back from a conference at ESO where the mood felt really exciting, I think, within planet formation, because we're beginning to change this picture a little bit of just this sort of isolated disk that we see in the millimeter continuum. And as we push ALMA to look at the gas and to look at more distant star-forming regions, we're beginning to understand really what the role of environment is for this planet formation process. So these things aren't isolated, but actually, as we go up through the scales, we can see that there's actually a sort of continuum of processes that lead to driving the evolution of these systems. And I think that's what I'm going to try and convince you of today. And for people that aren't necessarily engaged in planet formation directly, maybe your topics actually are more relevant than you might think. So just to give a sense of how these things are connected, I'm not going to go through the whole table here, but essentially the sort of star formation physics on different scales, and this is of course not a complete list of the different processes that might be relevant, but you know, things like the mass function of giant molecular clouds, the turbulent energy spectrum, all set properties that then have a role in driving disk evolution, and particularly relevant for this talk, the density of stars or gas, the local velocity dispersion, and the UV field all seem to have really strong influences on the planet formation process itself, and this can be through mass loss, dust inward drift, turbulence, gas dust temperature, chemistry, and winds, and all these processes are really important for understanding this sort of finite exoplanet population. So I'm actually just going to focus, just on the interest of time, I'm just going to focus on two processes. We could add more to this list, but a few relevant processes that sort of cover a lot of different phenomena. As external irradiation and photoevaporation, external photoevaporation of stars in high UV environments, and infall of gas from the surrounding ISM. I'm going to skip stellar encounters, but I'm happy to answer questions on them. So first of all, external photoevaporation. What is it? Essentially, we imagine that our star, our disk hosting star, is in a high UV environment. It's irradiated by high energy photons. And this causes a heating, this causes a thermal wind, a photodissociation region, and what we see here is what's known as a propylid, which is essentially a bright ionization front, which gives this sort of cocoon-like structure. The mass loss in the ring can be understood analytically if it's set by the ionizing photons, because we can just imagine that we have a continuity equation across the ionization front, and this depends on the sort of relative width of the photodissociation region through this parameter x here. But that's essentially set through the rate of ionization versus recombination balance. So we can understand the mass loss rate in this way. However, quite often we might expect actually that the sonic point is actually inside this neutral subsonic region. So the gas becomes supersonic inside the photodissociation region, and in which case actually we need to understand the microphysics in this photodissociation region. Okay, I've missed there's a slide missing, but essentially then we need to have models from PDR physics to understand what the mass loss rates is, and Tom Howarth has been doing a lot of work on this, and this is strongly dependent on what the dust content is in this photodissociation region. So we really need to understand things like the polyaromatic hydrocarbons and things like this that are becoming accessible with JWST. So what do typical UV environments look like? And this is relevant for understanding how this goes from our planet-forming regions that we're studying to the exoplanet population. Well, actually, if we think about the distribution of, in terms of the number of members of a star-forming region, this is actually typically dN/dm, if you like, the slope of the number of regions as a function of the mass of the region is parallel with a -2 slope. What this means is that you have an equal number of stars born in different regions of different mass. So between 100 solar masses and 1,000 solar masses, you have the same number of stars born as you do between 10 to the 4 and 10 to the 5 solar masses. But the regions are overrepresented at the low mass end, which means when we try and learn about planet formation, we're normally doing it at this sort of overrepresented region in sort of star-forming region space, and we end up learning our lessons from places like Taurus, which have very low UV luminosities. So we're not really necessarily, when we look at these disks, probing the sort of typical regions in terms of the external UV flux space. And does this have an impact on the disk? Well, we're pretty certain it does. We can actually see evidence, and we've known of evidence for quite a while, that this external UV environment does actually seem to affect the lifetime of protoplanetary disks. And we can see here Mario Garcello in 2016, but sort of republished in 2023. We can see the number of disks, the fraction of disks that still survive goes down as a function of the external UV environment. And we can see this in a variety of different regions. And we can also ask, what does this mean in terms of dispersal? And this remains an open question. But does this mean that we actually end up with a different dispersal mode? So this UV energy is being injected into the outer part of the disk, unbinding the disk. Usually we expect maybe a disk to be dispersed inside out by the internal UV photons. So are we seeing a different mode of dispersal? And I think that this is still not clear that this is the case, but this remains an open question for the future. What about the dust? So if we go back to ALMA data and we think about what is the dust mass of these planets doing. Really interestingly, actually, recently there's been evidence that the dust mass as a function of increasing UV flux is monotonically decreasing all the way down to sort of solar neighborhood average value of G0. And this is really interesting because it's suggesting that the millimeter grains, which is what is being probed by these ALMA observations, are being quite strongly affected despite the fact they're not the ones that are being extracted from the disk. So the winds are only entraining the small grains and the gas. So what's actually happening here? Is it just that we're reducing the reservoir of small grains, or is it that we're affecting the inward migration of the dust through pressure gradients, which has been suggested by Andrew Selick, for example, a few years ago? So this is still an open question about how this is actually affecting the millimeter dust. What's really curious about this as well is that actually we see that higher mass stars seem to be more affected by this process. So we see here, Karina Malko has published a paper showing that in Sigma Orionis that actually the more massive stars seem to have a steeper gradient in the dust mass as a function of the separation from a massive star than the low mass stars. And this is very curious because we'd expect the opposite to be the case. We expect a deeper gravitational potential around high mass stars and low mass stars. So why is this differential effect seem to be higher? Is this to do with internal physics, or is something else going on here that we don't understand? I'm just going to have a very brief word on disk chemistry because I think it's very interesting that now we're beginning to do this with ALMA and with JWST. We're beginning to get pictures of what the chemistry of disks are like, but we're at a very small sample size at the moment. But in the cases where this has been looked at, so with ALMA, looking at different molecules in the outer disk, and with JWST in the inner disk, and the sort of red point, the red points here and the orange points here represent these irradiated disks. Actually, we're not seeing that much difference. They look pretty typical in terms of their luminosity, in terms of these different molecular lines. But we're really at the point of like a few data points. So I think this is something that's going to be really interesting for the future and seeing if this holds. So there's a few open questions I've highlighted. I think particularly I'm really interested in how this millimeter flux is really influenced. I think we don't understand this. It's got to be in conjunction with all the other processes going on inside the disk. And what is the mode of the dispersal? And how does this affect low and high mass stars? So these are open questions facing external photoevaporation at the moment. And with the second part of the talk, I'm just going to talk about the capture of the interstellar medium, which seems to be becoming really a hot topic in planet formation. And we're beginning to understand that it seems to be playing a role throughout the disk lifetime. So there's been loads of evidence of infall in different disks. I've just chosen a couple of cases here. We see these much larger scales. So if you look at the scale bar in the bottom right here, we can see for different molecular line traces, actually we have a much more extended, messy structure than just the inner disk when we start going to the gas with ALMA. And this is really interesting because it's suggesting that this stuff is really connected to the disk. It's really infalling onto the disk. And this is for older stars. This is not just 0.1 million year old stars that we expect to still be in this sort of gravitationally collapsing early phase. And the timescale for the collapse is generally pretty short, right? So it's 10 to the 4 years. So this this is happening over such a short period compared to the lifetime of these disks, and we only have two options. Either these infalls are sustained by the environment, but it's difficult to do this for millions of year timescales, or we're missing most of them, right? So we're only seeing a small number of these things, and actually they're happening much more frequently. So this is a really interesting, the fact that we're seeing so many examples of this now as we begin to probe the gas with ALMA is really interesting. So with SPHERE, we've already seen some stuff using SPHERE for exoplanets. In planet formation, it's also driving this sort of change in the picture of planet formation physics as well. So in this is by Garifi et al. 2024. They looked at Taurus, they looked at Chameleon as well, a few different star-forming regions. And what they're finding is that 16% of this, and we can see some of these here, have these huge, in the scattered light, they have these huge structures. 3 minutes remaining, okay. So just to speed up a little bit on what we think might be happening here, well, this is actually an old idea of Bondi hole Littleton accretion going on throughout the disk's lifetime. So we can understand the Bondi hole radius is proportional to the stellar mass divided by the square of the local gas velocity. And what happens is that the gas is just concentrated into the stagnation point, and then low angular momentum material is accreted onto the star. And this actually leads to this relationship between the accretion rate and the stellar mass that we see. In a turbulent medium, we actually expect this to form a disk, as we see as well. There were several objections that I'm not going to go into originally for understanding, for this actually being the process that does drive disk accretion. So it's far from clear that that's what drives the accretion from the disk onto the star. But it does seem to produce, if we put this into the model with sensible densities and sensible velocity dispersions, this is some work I've done with Miriam Benisti and Sean Andrews, we can actually reproduce so that the back is a sort of model, a simple model, understanding the sort of turbulent fluctuations in the medium, and the red points are the observed data for disk mass, stellar accretion rates, and the accretion radius as well. And actually, we get really good agreement as a function of time in different regions for the disk properties. So this seems like something that could really be setting the disk properties rather than necessarily the internal processes necessarily. And this also implies that a huge fraction of these disks have been replenished at late times. So this has huge implications for how we understand dust evolution, planet formation, all of these different processes which you use this disk population as proxies for. And it's also injecting a substantial amount of turbulent energy into the disk. So very, very briefly, some warps are perhaps one evidence of this ongoing infall, and actually this is developing a lot of interesting results at the moment. We've seen actually one very interesting result that in edge-on disks, which are a nice sort of, in a sense, not an unbiased sample because we're just sort of randomly orientated. Among these edge-on disks, actually just through the inhomogeneities between the different sides of the emission and modeling this in a multi-wavelength way, we're seeing evidence of about 75% of disks having these warps, so offsetting the angular momentum vector between the inside and the outside. And this is also causing shadows, which are a huge fraction of disks are also associated with differences in the alignment between the inner and the outer disk. So I'm going to skip to some open questions briefly. It's still an open question that I think is very exciting for the field, and how is this late infall actually influencing the disk evolution? How is this related to the broader environment? Can infall in protoplanetary disk start to solve some evolutionary questions we have, for example, regarding turbulence? And then finally, so then just two very brief conclusions, I think. The point is that the large galactic scale is really an unavoidable consequence of star formation, and it's really important for planet formation. I think that that's undeniable now. The point is that there's also a huge number of unanswered questions, and I think we need a broad collaboration across different fields to unpick how these physics processes are related. So thank you very much.